Okay, the last part we're going to look at here are some extra periodic trends. We're going to look at reactivity and electronegativity. Okay, for reactivity, it's how easily an element reacts with another element to form a bond. That's how reactive something is. Okay, metals like to lose electrons to form bonds. So if we talk about where are the metals that are most reactive, well, wherever they're easiest to lose. So if they're easiest to lose electrons, okay, those ones are my electrons that are in the lower left, or my metals that are in the lower left. Okay, and the reason I'm going to say lower left has to do with your radius trend for electrons. Okay, these are the ones that have the largest radius. Since it's the largest radius, that means the electrons are furthest away. Electrons are furthest away, they're very easy to take, okay, over somebody else to come by and take, a non-metal to come by, okay? So these are ones that really are just not held as tightly, which makes them very reactive. So we're looking at things in the lower left again. So that's going to be something like francium, cesium, barium, radium. Those are all some of the more reactive elements overall, okay? That's why if you put potassium in water, that's a lot more reactive than sodium. And sodium in water is a lot more reactive than lithium. Okay? Along the same lines, this alkali metals, or the darker orange group, are more reactive than the alkaline earth metals, or the ones with magnesium. Okay? Magnesium has to kind of lose more electrons. All right? Plus, it's a little bit smaller in size, which makes it a little bit less reactive as well. Okay, so calcium is a little less reactive than potassium. You put calcium in water and it'll react, okay? It'll react a little bit better than magnesium, but it won't be more reactive than potassium. So we're on the very lower left-hand side. Okay, in fact, then to nonmetals, okay, nonmetals love to gain electrons to form bonds, especially ionic bonds. So where are the most reactive nonmetals? Those are actually in the upper right. We're kind of going with the opposite of size here, because since you're gaining, it really doesn't matter how big they are in terms of held as tightly or held not as tightly. Okay, looking at the number that you have to gain, so the less electrons to gain to be kind of a stable atom or a stable bond or a stable compound, okay, those ones are going to be the more reactive ones. So that's why we're saying upper right, so the less electrons to gain. If you look at chlorine versus, say, sulfur, okay, chlorine only has to gain one more electron, okay? Sulfur actually wants to gain 2 more electrons, and we'll talk a little more about that in the next chapter. We're talking about valence electrons and things like that, okay, in your core. But chlorine really only wants to gain 1 to look like argon and be a noble gas. Sulfur has to gain 2 to look like argon and be a noble gas. So chlorine is a little more reactive than sulfur. The opposite then goes with size, okay? Fluorine is actually way more reactive than iodine. Okay, and the larger ones actually are harder to interact with things because your nuclei are going to be further apart. So fluorine that wants to gain somebody else's electron is very tight, okay, very small. It can actually very easily then interact with another element. Okay, but iodine being much larger, trying to gain an electron, is going to be a lot harder to interact with an element. So kind of I talk about chlorine versus sulfur there in size. Okay, we have 1 negative or gaining 1 electron versus one that has to gain 2 electrons or more. And then I talked about size, okay, at the bottom, they are larger and interact not quite as well. Okay, the last thing we're looking at is electronegativity. All right, electronegativity, when we're talking about this, okay, when atoms bond, they share, lose, or gain electrons. That's going to be the study of our next few chapters after this one, all right? So this is our kind of segue into the next one, all right? So they share, lose, or gain electrons, okay? And electronegativity then kind of measures how attracted electrons are to a certain atom in a bond. So here we're talking about a bond, okay? So I'm dealing with maybe a hydrogen-chlorine bond, okay? So we do these little lines in between, talk about when they're bonded together, okay? We'll talk more about this later, okay? But I have some electrons here in the middle, and chlorine tends to want to have electrons around it a little more than hydrogen does. So these electrons, okay, are actually going to sit a little bit closer to chlorine. So if I'm going to redraw these, okay, they're actually going to sit a little closer to chlorine than they would to hydrogen. And like I said, we'll talk a lot more about this later. But right now we're dealing with electronegativity being how attracted the electrons are to one or the other atom when they're bonded together or bonded to something else. Okay, and your most electronegative element is going to be fluorine. Why? Just because it is. Okay, so if I have an SiCl bond, which one's more electronegative, and what does that mean in terms of electrons? Well, if I look at Si and Cl, Cl is much closer to fluorine than Si is, just in general vicinity. Okay, so that means that chlorine is my more electronegative one. So what that means is that the electrons between Si and Cl, okay, will spend more time around the chlorine than the Si.